Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be finishing up our lecture on electrostatics and magnetism. We've made it to the final objective, which is titled Magnetism, and understanding magnetism is essential because, like electrostatics, it plays a crucial role in many areas of physics. Any moving charge creates a magnetic field, and this field can interact with other moving charges or magnetic materials. Unlike electric fields, which are produced by static charges, magnetic fields arise only when charges are in motion. This is a fundamental difference between electric and magnetic fields. Now, the strength of a magnetic field is measured in Tesla. This is the SI unit for magnetic field strength. A Tesla is quite a large unit, so we often encounter smaller fields measured in micro or millitesla in everyday situations. In addition, magnetic materials are classified into three main categories based on their response to an external magnetic field. We have diamagnetic, paramagnetic, and ferromagnetic materials. Diamagnetic materials are weakly repelled by an external magnetic field. In these materials, all of the electrons are paired, meaning their magnetic moments cancel each other out. When exposed to an external field, diamagnetic materials develop a small, temporary magnetic moment in the opposite direction of the applied field. But this effect is weak, and it disappears when the external field is removed. Then we have paramagnetic materials. These are weakly attracted to an external magnetic field. These materials contain unpaired electrons, which means they have permanent magnetic moments. However, because the magnetic moments are randomly oriented in the absence of a magnetic field, the materials do not exhibit strong magnetism. When an external magnetic field is applied, the magnetic moments align slightly in the direction of the field, and that causes the materials to be weakly attracted. Last, we have ferromagnetic materials. They exhibit the strongest magnetic behavior. In these materials, the magnetic moments of unpaired electrons can align in the same direction even without an external field. This results in a permanent alignment of the magnetic moment, and the material retains its magnetism even after the external field is removed. Common examples of ferromagnetic materials include iron, cobalt, and nickel, which can be magnetized to create permanent magnets. Now, we've discussed the types of magnetic materials. Let's move on to how magnetic fields are generated by current carrying wires. And we're going to start by discussing long, straight wires. A magnetic field is created around a long, straight wire when a current flows through it. The strength of the magnetic field at a distance r from the wire is given by this equation here. In this equation, B is the magnetic field strength, and it's equal to mu naught, which is the permeability of free space, multiplied by I, which is the current flowing through the wire, divided by 2 pi r, where r is the distance from the wire. The magnetic field produced by the current forms concentric circles around the wire, and the direction of the field can actually be determined using the right-hand rule. If you point your thumb in the direction of the current, your fingers will curl around the wire in the direction of the magnetic field lines. We also have circular loop wires that we want to discuss. So something similar occurs here when the current flows through a circular loop of wire. The magnetic field at the center of the loop is given by this equation. Here, B is the magnetic field strength. It's equal to mu naught, which is the permeability of free space, and it's multiplied by I. This is the current flowing through it, and this is divided by 2r, where r is the radius of the loop. The magnetic field is going to be the strongest at the center of the loop and weaker as you move away from the center. Keeping this information in mind, let's go ahead and tackle a practice problem. This problem says, suppose a wire is formed into a loop that carries a current of 0.25 ampere in a clockwise direction as shown here. Determine the direction of the magnetic field produced by this loop within the loop and outside of the loop. If the loop has a diameter of 1 meter, what is the magnitude of the magnetic field at the center of the loop? Now, to determine the direction of the magnetic field produced by this loop within the loop and outside of the loop, we need to use our right-hand rule. So we're going to use our right-hand rule, and specifically, we're going to align our right thumb with the current at any point in the loop. So I'm going to start here. We know that the current moves in this direction, so I'm going to align my thumb in this direction, and then I'm going to extend the rest of my hand like so. This is a really ugly picture, but I hope you get the gist. Align your right thumb with the direction of the current, and then loop your fingers. When you encircle the wire with the remaining fingers of your right hand, your fingers should point into the page within the loop and then out of the page outside of the loop. So again, when you encircle the wire with the remaining fingers of your right hand, after you've aligned your right thumb with the current at any point in the loop, you're going to notice that your fingers should point into the page within the loop and then out of the page outside of the loop. Now, to determine the magnitude of the magnetic field at the center, we're going to be using this equation for circular wires. The magnetic field is going to be equal to mu naught multiplied by I divided by 2R. Now, mu naught, this is the permittivity permeability of free space. This is a constant. It's equal to 4 pi times 10 to the minus 7 Tesla times meter per ampere. And then we're going to multiply this by the current, which we're given as 0.25 ampere. And then this is going to be divided by 2 times the radius. Now we're given the diameter. The diameter is 1 meter. The radius is half of the diameter, so 0.5 meters. Here, we can go ahead and begin to do this calculation. So in the denominator, 2 times 0.5 is just equal to 1. So our denominator is just equal to 1. We can just worry about our numerator. Here we have 4 pi times 10 to the minus 7 multiplied by 0.25. 0.25 can be rewritten as 1 over 4. And you notice that the 4's cancel out. And our answer is pi times 10 to the minus 7, which is equal to 3.14 times 10 to the minus 7 Tesla. So that is our final answer. Now that we've answered this question and we understand how magnetic fields are generated, let's explore how they exert forces on moving charges. One key point to remember is that magnetic fields only exert forces on moving charges, unlike electric fields, which can act on both stationary and moving charges. When a charge moves through a magnetic field, a magnetic force is exerted on it. The magnitude of this force depends on several factors, including the charge of the particle, its velocity, the strength of the magnetic field, and the angle between the velocity vector and the magnetic field vector. The force can be calculated using this equation here, where FB is the magnetic force, and it's equal to Q, which is the charge of the particle, multiplied by V, the magnitude of the particle's velocity, multiplied by B, which is the magnitude of the magnetic field, and multiplied by sine theta, where theta is the smallest angle between the velocity vector V and the magnetic field vector B. Let's break this down. The magnetic force It depends on the product of the charge and the velocity, meaning that a higher charge or a faster moving particle will experience a stronger force. It also depends on the strength of the magnetic field. Now, this term sine theta, that indicates that the force is maximized when the angle between the velocity and the magnetic field is 90 degrees, because sine 90 is equal to 1. This means that the magnetic force is greatest when the charge moves perpendicular to the magnetic field lines. On the other hand, if the particle moves parallel to the magnetic field, then theta is equal to 0, and sine 0 is equal to 0, so that means the force will also be 0. Now, to determine the direction here, we're going to use another form of the right-hand rule. So to determine the direction of the magnetic force on a moving charge, the first thing you want to do is you want to position your right thumb in the direction of the velocity vector. Then you want to put your fingers in the direction of the magnetic field lines, and your palm will point in the direction of the force vector for a positive charge, whereas the back of your hand will point in the direction of the force vector for a negative charge. Let's put this into effect by tackling a practice problem. This problem says, suppose a proton is moving with a velocity of 15 meters per second towards the top of the page through a uniform magnetic field of 3 Tesla directed into the page as shown here. What is the magnitude and direction of the magnetic force on the proton? Describe the motion that will result from this setup, and note that the charge of a proton is 1.6 times 10 to the minus 19 coulombs, and its mass is 1.67 times 10 to the minus 27 kilograms. Now, to start solving this problem, the first thing we want to do is determine the magnitude of the force, and we can do that using this equation right here, QVB sine theta. Now, theta is going to be equal to 90 degrees. Your velocity is upward, your magnetic field is into the page. This gives us an angle of 90 degrees, and sine of 90 degrees is just equal to 1. So our equation here is just QVB, and we have all 3 of these variables, so we can go ahead and plug them into our equation. The charge of the proton is 1.6 times 10 to the minus 19 coulomb. Our velocity is 15 meters per second, and the strength of our magnetic field is 3 Tesla. Now what we have here is 15 multiplied by 3, this is 45. 45 multiplied by 1.6 is 72, and we can't forget this times 10 to the minus 19. We can alternatively write this as 7.2 times 10 to the minus 18 Newton. Now that we've determined the magnitude of the force, we need to figure out the direction. And we can determine the direction using the right-hand rule. So I'm going to assume that you have this drawn out on a paper on your desk. You want to take your right hand, you want to align your thumb with the direction that this proton is moving in, upward. And then the rest of your fingers are going to be pointing downwards because the magnetic field is directed into the page. So you're given the gesture of like, what are those towards your paper? Now you need to figure out the direction of your palm. The force is in the direction of your palm, which should be to the left. Now note that V and your force that you just determined the direction of, they're always perpendicular to each other. This implies that uniform circular motion will occur in this field, with this force pointing inward towards the center of the circle. Now, if the centripetal force is the magnetic force, then we can set these 2 equations equal to each other and solve for R, right? So we're saying that centripetal force is going to be equal to our magnetic force. The equation for centripetal force is mv squared over r. Our equation for our magnetic force is qv mVb sine theta. Really quickly, we can get rid of 1v on both sides. Sine theta, we said, is equal to 1, so we can get rid of that. What we're left with is mv over r is equal to qb. We want to isolate for r. When we do this, this gives us r is equal to mv over qb. Now we have all of this information. We can go ahead and plug it in. The mass of the proton is 1.67 times 10 to the minus 27 kilograms. Velocity is 15 meters per second. This is divided by the charge of the proton, 1.6 times 10 to the minus 19 coulomb, and the strength of our magnetic field is 3 Tesla. Now this is going to give us approximately 5.2 times 10 to the minus 8 meters. This is alternatively written as 52 nanometers. So the proton will move in a circle with a radius of 52 nanometers. And that's the answer to this problem. Now we want to discuss forces on a current carrying wire and elaborate on that a little bit more. When a wire carrying an electric current is placed in a magnetic field, the wire experiences a force from the field. This force depends on the current in the wire, the length of the wire in the field, and the orientation of the wire with respect to the magnetic field. The magnitude of the force on a straight current-carrying wire in a magnetic field is given by this equation here. FB is the magnetic force. It's equal to I, which is the current flowing through the wire, multiplied by L, the length of the wire, multiplied by B, the magnitude of the magnetic field, multiplied by sine theta, where theta is the angle between the direction of the current and the magnetic field. Now, this term, sine theta, it introduces an important aspect. The force depends on the angle between the wire and the magnetic field. If the current flows perpendicular to the magnetic field, then theta is equal to 90, and the force is maximized because sine of 90 is equal to 1. If the current flows parallel to the magnetic field, then theta is equal to 0, and there is no force because sine of 0 is equal to 0. Now, the same right-hand rule can be used for a current-carrying wire in a field as for a moving point charge. Just remember that current is considered the flow of positive charge. So let's go ahead and tackle our last practice problem for this lecture. This problem says, suppose a wire of length 2 meters is conducting a current of 5 ampere towards the top of the page and through a 30 Gauss uniform magnetic field directed into the page. What is the magnitude and direction of the magnetic force on the wire? Now, this is a great problem for us to discuss the conversion between Tesla and Gauss. 1 Tesla is equal to 10 to the 4 Gauss. So here, when we're given 30 Gauss, this is equal to 3 times 10 to the minus 3 Tesla. This is the strength of our magnetic field. Now, to calculate the magnitude of the magnetic force, we're going to use our equation for current carrying wires and determining the force on those. This is going to be equal to ILB sine theta. Now, sine theta, this is going to be equal to 1 because theta is equal to 90 degrees. Why is it equal to 90 degrees? Let me work you through it. The wire is conducting current towards the top of the page, and the magnetic field points into the page. Therefore, the current is perpendicular to the magnetic field, and the angle between them is 90 degrees. Sine 90 is equal to 1, so our equation shortens down to ILB. And we actually have all 3 of these variables, so we can go ahead and plug them into our equation. I is the current. We're given that as 5 amperes. The length of the wire is 2 meters, and the strength of the magnetic field is 3 times 10 to the minus 3 Tesla. 5 times 2 is 10. 10 times 3 is 30. And we can't forget about this times 10 to the minus 3. We can alternatively write this as 3 times 10 to the minus 2 newtons. So that is the magnitude of the magnetic force on the wire. What about the direction? To determine the direction, we're going to use our right hand rule. Your thumb should point up the page, all right? And then your fingers, the rest of your fingers should point into the page in the direction of the magnetic field. Current, this is a flow of positive charge. So the force is in the direction of your palm, which is to the left. So our answer for magnitude of the magnetic force, 3 times 10 to the minus 2 newtons, and the direction is to the left. And with that, we've completed our lecture on electrostatics and magnetism. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.